Hello guys, in this video I'm going to show you how to solve all task scheduling orders problem. So there are n tasks labeled from 0 to n-1. Each task can have some prerequisite tasks which need to be completed before it can be scheduled. Given the number of tasks and the list of prerequisite pairs, write a method to print all the possible ordering of tasks, meeting all prerequisites. Right. So this problem is pretty much the same as task scheduling, right? But for task scheduling problem, all we need to do is to return true or false whether we can schedule an ordering of tasks that meet the requirements, right? But for this problem, we need to print out all possible ordering of tasks, right? Which makes this problem so much harder, I think. So let's see how we're gonna solve it. All right. So here we have an example. 2, 3. We have a list of prerequisite. Here means in order to do task 2, we must do task 3 first, right? 2, 3. Same here. 2, 0, 2, 1, right? So it means we can represent our problem in a graph problem, right? Okay, so here the output, we have 2 possible ordering, the total of 4 tasks, right? Which is 0, 1, 2, 3, right? So if I represent a problem, it should be 2.2, right? Oh, maybe it's better to use paint here. Want to model our problem a bit. I think 2 to 3. Okay. 3 to 0. 2 to 0. And 2 to 1. For this kind of problem, what we need to keep track of is a graph, right? We need to represent our problem into a graph, and we need to keep a graph and also a map of incoming vertex, right? So for this one, here is our graph. Also, we need to keep track of our dependencies map also. So for example, wait a minute, 2 to 1 instead, right? So we need all the vertex, right? Here is our map of incoming, right? Incomings. Incoming vertex, right? So for example, vertex 0 has two incoming vertex, right? As you can see, there are two vertex that pointed to 0, right? So 0, there, whoops, there are two, right? Oh, let's use another color. For vertex 1, there's only one vertex pointed to 1, right? For 2, there are 1, but for 3, there's 0, right? So it means for the first vertex in our ordering, the only choice is this guy, because um, we want to put our next vertex in our ordering only if um, only if that vertex has 0 dependencies, right? So for the first, so our problem here is to print out all the orderings. Uh, so maybe we can do some backtracking here, I think. So for the first, our goals is to print out. So one ordering will have a total of 4 slots, right? Something like this. Here's one slot. Okay. 4 slot, right? So for the first slot, let's say for the first slot, for second slot, third slot, fourth. For the first slot, we have one choices, right? Which is 3 here, right? So let's say so after putting 3 into our ordering, right? Put 3 here. We need to clean up the 3 here. So right. So after putting 3 here, we don't care about 3 anymore. So I will remove 3 out, and any vertex that coming from 3 as well, right? So we no longer have 3 in our graph. Also, we need to update our incoming maps, right? So what changes here is the incoming of 0 and 2. So 0 now has only 1. Whoops. Whoops. Brushes. Okay. And 0 now. No. 2 now has 0, right? As you can see, there's no vertex pointing to 2 now, right? So we update our incoming maps, right? So as you can see, for the next slot in our ordering, so we're done here. So So our incoming map has now 3 entries, right? For the next slot here in our ordering, the choice that we have here is we have only choice here, which is 2, right? We have 2 here. The only choice that we have here is 2, because it is the one that has 0 incomings. It has 0 dependency. So we want to start. We want to put the next vertex that has 0 dependency in our ordering, right? 3, 2. Okay. So after putting 2 into our ordering, I need to clean up a bit. I remove 2 out. I also need to remove any dependency, any vertex that coming from 2 as well. It goes out. Now also I need to update our incoming maps, dependency map. Now 0 has 0 incoming vertex, right? 1 has 0 as well. And 2, we're done with 2 now. 2 go to the second slot in the ordering, so we pick it and we remove it, right? So now what is left is 0 and 1 both have 0 dependency here. So for the next both of these can be, either of these can be the next candidate for the third slot, right? So it means here in the third slot we have 2 choices, right? It means here there are 2 choices here, which is 0 and 1, right? So here we can have 0 and 1, 2 choices, right? So it it is clear that it's pretty clear that if we pick 0, then the last one will be 1. The last slot will be 1, and if we pick 1, the last slot will be 0, right? So it means here so why is that? So for example, if we pick 0 here, we remove 0 from we put it in our ordering, we remove it from the graph, we update our incomings here, but there's no vertex that coming from 0, so there's nothing to do here, right? So we just go to the next uh, next we just go to the next level, we find the next vertex for the last slot in our ordering. So here after picking 0 here, what is left in our dependency map is 1, right? So we just pick the last one and put it here, right? So we finish when our our source list has no item anymore, right? Uh, so at any point in time, we need to keep track of a source list, which is a list of possible choices, a list of candidates that that is available for uh, that is available to pick from, uh, so that we can select the candidate vertex and put it to the to the next slot in ordering, right? So for example here, um, in the first slot, in the first slot, here is our original map 2110. Uh, the only choices is 3, right, as we discussed earlier. So we need to remember all the choices here, which is uh, we have one choices, 3 here, right? So for example, if here we have more than one choices, we can look through all the choices here, right? We look to all the choices here. So as we go down the trees and we come back here, then we can so for each choice, we go down the trees, we come back here, then we go to the next choice, right? So for example here, after picking 3 here, for the next choice we have only one choice as well, right? But for here we have two choice, which is 0 and 1. So if we pick 0 here, the only choice we'll have is 1, and if we pick 1 here, the only choice left is 0. So that is uh, how a problem work, right? So let's try to code it out, right? So pretty much the same as any problems in our topological sort. We need two maps, right, to keep track of um, our to represent our problems, right? We need to build our map, our graph, and also the dependencies map as well. Okay. Uh, okay. Okay. For the graph, it is a map, right? For the dependency, let's call it incoming, right? So two parameters here we have is the total of tasks and the prerequisites list, right? So let's initialize our graph and incoming list here. So for let of task, let's task of let's say task. Here's array of tasks, and here so this will so task here will be from 0 to, for example, task here is 10, then the total of tasks is 10. Here it means I want to iterate from task 0 to task n minus 1, right? So for each task here, I want to set it, right? I want to initialize it. The key will be the task itself, and the value will be a list, right? A list that the that current task is pointing to, right? Initialize will be empty array. And for incoming, I also need to set the task. Initially, there's 0, right? There's zero dependency. Okay. What next is after initializing our two maps here, I need to actually put the data into two maps here using prerequisite. I'm gonna loop through let here for let our prerequisite will be a list of arrays, right? Each array has two elements, the source vertex and the destination vertex. So I'm gonna iterate through the prerequisite, right? The array, let's see. I'm gonna use no, iterate to each one, and I'm gonna destructuring. This is gonna be one item, right? An item will be an array of source and destinations, right? So let's say so for each pair of prerequisite, I'm gonna add it to the I'm gonna get the source, right? So this will return an array. This will return an array that the source vertex is pointing to, right? So I'm gonna push what? Put the destination here to this list of vertex, right? That source is pointing to. Also incoming, right? Incoming. I want to get. I want to set for the destinations, right? Destinations. I want to increase. I want to increase it by 1, right? So I need to the current value, right? I need the current value. So incoming get the destination task, right? And this plus 1, so set to the destination vertex. So So by doing so, we increment the incomings of destination by one. Right? Okay, next here I need to I need as we discussed earlier, we need to keep track of a list of the sources, which is all the candidates for the next slot, right? So here I will have to fill the source candidate. That's a candidate list. It will be more intuitive here. The candidate list. Uh, our candidate initially is an empty array. So I will iterate to every to the incomings for uh, because um, incomings is a map, right? So in order to iterate to it, I'm gonna use entries method so that each item will be destructured into what the vertex. The key is a vertex. The destination vertex. Let's say the task, and the value will be the number of dependencies. So if I want the task with zero dependency, right? If number of dependency is zero, then I'm gonna add it into the candidate list. I'm gonna add it to here, candidates task. This will be available to pick, available to select, to be selected for the next slot, right? So what I was doing here is kind of like doing depth first search, right? And we kind of like backtrack here from here to kind of um, to kind of list out um, all the possible choices here, right? We want to kind of like uh, so right. So for any problem that um, requires to print all the possible tasks, you might think of this method, right? This approach, which is we we gonna we gonna search for we kind of like run to all possible choices by uh, using recursions here, right? To go for every possible choices. So here, actually, what we was doing is using recursions, right? So what kind of state we need to keep track of between the recursive calls here. So assuming that our recursive functions will be DFS, right? This one will will go to the depth, right? To look for every possible choice, right? Go all the way to the leaf node, right? Until what? Until we have out of choices. So for example here, we what left here is one, right? So after picking one, we have no other choices. It means we reach the leaf node here, so we must come back, right? So this will kind of brute force uh, every possible choices, right? So maybe we can, this will return all the choices also, so I will return it. This will remember the possible ordering, then return it, right? What we need here is, let's say, we need to, here we need to get access to the graph and incomings, of course, right? Graph and incoming. Incomings, okay. And we need our candidates list as well, candidate list. And what else do we need here? What we need here is actually the current, the current, what is that? The current, the the current ordering, right? So for example, here is 3. We pick 3 to our ordering. So here we add 2 to the ordering. So we have 3 and 2 like this. So if we pick 0, we have 2, 3, 2, 0, right? But if we pick 1, we have 3, 2, 1. Okay, it means, as you can see, we are keep track of the current ordering, right? 3, 2, 0. Here we pick 1, right? 1. But here we have 3 coming from this range. 3, 2, 1, 0. Oh, okay. So it means we need a current ordering. Current, or let's say it current, right? Current. And we need all ordering as well. Let's say it all. But this I probably don't want to pass it here because it will be an default parameter. It will exist only in the context of DRS, right? So here we have graph, incoming, candidate, and current. If I don't pass it, it will be empty array. Or if you don't pass it, I will have an empty array as well. So I don't need to pass it here. So this one will return all, right? So that we can return whatever DMS returning here, and that will be the answer for our final questions. Return all here. So now coming to our logic of recursive functions, right? For the recursive functions here, so we want to stop the base case. We want to stop when, probably when our ordering here, the current ordering, the size of current ordering is equal to the size of map, right? Or the size of incoming maps or graph maps, right? So if the current dot length equal to graph, from what I remember, new map here, we have the size attribute, right? Is return the size of graph, right? Size here. If this is true, it means I completed one ordering here, right? So I want to add the current, whatever the current is, but don't want to add the reference. I need a copy because the current here will be changed between the call also. I need a copy of it, right? So after put the current ordering to the or, I will return it, right? So from here I will return back to 0 here, the previous level. So we come back to the previous level. At this level, we've done with this branch 0 here, right? So the next choice 1. So we go this way, picking 1 and go down further until this is size of current ordering equal to current size of graph, right? So here we need to iterate for every candidate. So for each vertex with task of candidates, I need to add the current task to the ordering, to the current ordering, right? So it means for this task, I will add it to current ordering, right? What else I need to do here? After putting it here, I need to go further down to 3. So probably I want to call the graph here, the incoming here, the candidates current all. But will we, and this, is there anything will be changed here? Is there anything we need to update before going there? The graph is probably not. It's gonna be static for every recursive call, right? But the incoming we probably need to update it, right? the candidates as well, because here we add tasks to the current ordering. So it means it is no longer to be a candidate for the next recursive call, right? So here it is probably not the candidate here. So let's say new candidate. So new candidates, right? Will be I'm gonna filter from the candidates here, right? I'm gonna filter the tasks here out of the candidates and return a new list of candidates, right? So kind of I want to isolate the choices from previous call to the next call. The candidate filter here, let's say C for the candidates. I'm gonna filter. I'm gonna keep all the candidates that is not the task that I push to the current ordering, the task that I pick here, I selected here. So the new candidates list will go to the next. This one will not contain the task here, right? The current is updated here. The all will be a reference, right? So that after all we can return it here. We need to update the incomings as well, because here we selected the task, right? So probably we want to update all the we want to update the incomings map here, all the tasks coming from all the vertex coming from the tasks here. We need to kind of eliminate it from the incomings here. So probably for let incomings is a map, right, of incomings. To iterate, I'm gonna use entries method. So each one of these will be tasks and number of dependency. So let's say now probably here we can use a graph itself, right? Um, mm, because I only care about the I only care about the vertex that coming from a certain uh, only care about the uh, I only care about the edge, the edge coming from certain uh, coming from this current task, right? So probably I will use the graph itself. So for let destination of graph, I'm gonna get the task here. This will return a list of vertex that the this task is pointing to, right? So for each of these destinations vertex, I want to update it in the incoming map here. I want to decrement it by 1 because we've selected the task here. So any vertex coming from the task, I want to eliminate it, right? So incomings, I want to set the destinations. It would be whatever it is right now, -1, right? So if this one, if it reaches 0, right, it can be a next candidate, right? So here, if I wanna add it to new candidate, push. Okay. So this only thing left here is the backtracking part, right? Backtrack here. As you can see, as we coming back from from the from here, from the recursive core here to the previous level, we want to restore the state of we want to restore the state of current, right? So after going current here, I will pop it from the current. So for example here, let's say here 3, 2. Here we have two choices, right? 0 and 1. If we go for 0, right? We add 0 to the current ordering. So we go down the tree. So after coming back here, I want to restore it to the original state, which is 3, 2, right? So I need to pop 0, the last item that I popped, and that I push in at this level. I want to pop it out and add the next choice here in, which is 1. So after here I pop it out. What else I need to do here is properties, this um, because we add back the task here. The backtracking part here is actually we reverse what we do here to restore the original state before um, restore the original state so that uh, we can take the next choice in this candidate list, right? So it means whatever changes that we made here, we need to restore it, right? So the new candidate here is a local variable, so it will not affect the next choice, but the incomings here is changing, right? So we need to restore it, right? So I just copy whatever it here. So I'm gonna, because here we decrement by 1, so I want to increment by 1 here instead. This will not, we don't need this one. So I think that is it for this problem. Let's run a test. Just 16 3. Let's see, is there any mistake that we make here? Yes, it works. Let's say, to double check it, I will return empty array to make sure that the test is actually running the code that I wrote here. Okay, that's fine. It works. So it's been a very long video already. So uh, if you're still watching now, so thank you. So see you in the next one. Bye.